Hi there, Unit 1, Lesson 2, we will learn all of the parent functions that we're going to study this year, including a refresher of the main parent function you learned in Algebra 1, which was the linear parent function. So what we're going to do is we're going to set the foundation for the rest of the school year. So we're going to learn how to, given an equation that you're going to memorize, create a table for each parent function, which then will allow you to graph the parent function, and then you'll be able to answer characteristics about the parent function. So that's a process we're going to go through for every single one of these. We're going to start out with one that you're very familiar with, hopefully, which is the linear parent function. So what we consider our parent is just y equals x. You can also think of that as f of x equals x. Again, f of x is just fancy for saying y. When we create a table, something you want to be able to do is you want to be able to include some negative, some positive, and 0 as your inputs. So let's begin with, let's say, -3, -2, -1, 0, 1, 2, 3. So these are inputs you should be able to come up with that include a little bit of everything. Then what you will do is you have a formula in front of you. You have an equation that you can use to evaluate. Well, with the linear parent function, we know it's pretty straightforward. But let's just model this, that if we go f of -3, what we're really saying is we're plugging in -3 in the place of x. Well, when I do that, it's just equal to -3. F of -2, therefore in this case will yield -2. And as we know with the linear parent function, our inputs are equal to our outputs in the parent function. We want to make sure we have accurate graphs, so we would then go ahead and just graph this accurately. And after we have the graph in front of us, then we should be able to answer any characteristics following this function. So here we go. Our x-intercept, just a refresher, is where we hit the x-axis. In this case, the origin at 0, 0. Our y-intercept is where we hit the y-axis, so also 0, 0. Our domain, because we're going arrow to the left, arrow to the right, our domain is all real numbers. However, it is asking for interval notation. So that would be -infinity to infinity. Also, before you would have said the range is also all real numbers, but we're going to do it in -infinity to infinity. We're going to skip end behavior. We will come and study that here in the next lesson. Then we'll revisit all our parent functions and fill that out. So we will skip that for now. As far as asymptotes are concerned, when we get to functions that do have asymptotes, I will let you know and we'll discuss how we find them and what they mean. But until now, until we get to one, we'll say none. As far as a maximum or a minimum, that's referring to the highest point on the graph or the lowest point on the graph. Because our range is -infinity to infinity, we don't have a low and we don't have a high. So this would be also none. There's not a set point that we can say that satisfies that. And then let's think about symmetry. So if you think back to geometry, usually you would say you're symmetric across the x-axis, you're symmetric across the y-axis. Well, with a line, if you fold your paper vertically, it doesn't quite fall on itself. If you fold your paper horizontally, it still doesn't quite fall on itself. But if you fold your paper twice, it will do that. So what we say here is that it's symmetric across the origin. And that's the linear parent function. So this is the process we will follow with the rest of these. If you are watching this for learning purposes, my recommendation is that after I write down the equation, you practice yourself going through this process, then coming back and watching the video to see if you did it correctly. So for example, let's talk about a quadratic now. Our quadratic parent function equation will be this: f of x equals x squared. We're going to follow the same pattern. We're going to use some negatives, use some positives, and always want to know what's going on at 0. So if you feel confident filling this table on your own, graphing and then filling out the information, I recommend you do so and then come back and watch the rest of the section to check and see if you know what you're doing. That way you're already practicing, getting ready to learn these parent functions. Here we go. So what we want to do is we want to do f of negative 3. What this means is that we are inputting negative 3 in the place of x. Always parentheses just to be safe when you are inputting a value. So that's negative 3 squared. Well, that means negative 3 times negative 3, which is then positive 9. We would proceed in the same manner. That'd be positive 4. One. 0 squared is 0. And then so on, we would get 1, 4, and 9. Let's carefully graph these values. So we have 0, 0, 1, 1, 2, 4, and 3, 9. If you recall from Algebra 1, you should be slightly familiar with the quadratic parent function. You might recall its graph being called the parabola. We create a U shape here. Make sure you have a nice U shape on your graph. So if you're ever asked to create the parent function of a quadratic, this is the table, this is the graph, and you want to make sure you include all of those values to have a nice and complete graph. Now, this graph in front of us should be all the information we need to fill out the bottom part. So still 0, 0 for both of our intercepts. Our domain, there's an arrow going on the left and an arrow going on the right, so this is still all real numbers. However, our range begins at 0. There's nothing below that. And it goes on to infinity. So first of all, 0 is a possible y value. So we will go ahead and include it. And then we go on to infinity. Again, we'll come back to end behavior. The quadratic parent function does actually have a minimum or a maximum. In fact, it is a minimum. The lowest value on this graph is 0. Now, we will only include the y value because if we're talking about a maximum or minimum, we're talking about high versus low, and our lowest here is 0. So therefore, we have a minimum at 0. If you were to fold your paper vertically, it would fold right on itself, meaning this has a symmetry across the y-axis. Now, what you could also say is think of the y-axis as a vertical line. Vertical lines are x equals line. So I could also say across x equals 0. Because as soon as you move your parabola around, it's no longer across the y-axis. It could be whatever cuts it in half. All right, let's proceed. The next one we're going to look at is absolute value. So this might be the first time you've seen the absolute value parent function. Its equation is the following. F of x equals absolute value of x. That's how we read that, those vertical bars. Think of absolute value as distance, but first let's go ahead and still, same values, -3, -2, -1, 0, and then 1, 2, 3. So usually the way I like to explain absolute value is that absolute value behaves a lot like distance. So for example, if you're on a number line, you're traveling positive direction 5 steps, for example, then you would say, I went 5 steps to the right. If you're traveling left on your number line, even though you're going left, so technically you're going towards negative numbers, you would still say, I went 5 steps left. So here's what happens with the absolute value. When you input, so for example, f of -3, then whatever comes out of the absolute value is always a positive number. So absolute value of -3 is +3. Absolute value of -2 is +2. Then 1, 0, 1, 2, 3. Let's go ahead and graph this. So we have 0, 0, 1, 1, 2, 2. Notice very much so linear behavior. In fact, there's a connection between lines and absolute values. So that's exactly what's going to continue doing on the right. However, on the left, it's still linear behavior, so it's like two pieces put together. In fact, that is what an absolute value is, two lines pieced together. And it creates this V-shaped like graph. So our absolute value will always look like a V. All right, same pattern. So again, you could pause the video and try filling out the rest on your own and then come back. Still 0, 0. You'll notice a lot of these are in common because they're our parent functions. We haven't transformed them. We haven't moved them around. Our domain, we're talking about arrow to arrow. So we're also going to have all real numbers still. Our range starts at 0 and it goes to infinity. So similar to a quadratic, we say 0 to infinity. Still no asymptotes. And then just like a quadratic, this has a minimum at 0. If we were to fold this vertically, this would have a symmetry also across the y-axis, which we said can be rewritten as across y or x equals 0. So thinking of the x-axis as a vertical line. All right, let's continue. Our square root parent function. This function you might have seen in Algebra 1 or geometry, but you might have not graphed it. So the equation of it might look familiar. It is f of x equals square root of x. Now if you're copying this down as I go, don't copy just yet. Just pay attention. So typically we would say -3, -2, 0, 1, 2. Oops, sorry, skipped my -1. And the best way I can explain a square root of x is this. You ask yourself, what times itself gives you that value? and that's what you would put in there. So in other words, when you plug in a 1, for example, so let's do f of 1. I'm asking what times itself gives me 1. So since 1 times 1 is 1, that answer would be 1. Now if I try to do f of 2, then I'm asking square root of 2. So what times itself gives me 2? It's not pretty. It is a decimal. It's not a nice answer. So for a parent function, we want to use as pretty as answers as we can, and we want to keep our values nice. So for that reason, when it comes to the square root, this table doesn't work for us. We use something different. So 2 doesn't quite work for us. Let's think about the next thing up that we can take the square root of. And hopefully you're thinking 4. So here's what that means. If I use 4 as my input, square root of 4 is what times itself gives me 4. Well, that's 2, because 2 times 2 is 4. Then I try to go one more up, so f of 9 would be our next one. So square root of 9, meaning what times itself gives me 9, which is 3. Let's back up to 0. F of 0, square root of 0 means what times itself gives you 0, so the answer is 0. And then back up one more step. So let's see what happens with this, f of negative 1. This is asking what times itself gives you a negative 1. Well, think about it. If you take two positives and you multiply them together, you're going to get a positive. If you get two negatives and multiply them together, you will also get a positive output. So for that reason, we're not able to take the square root of a negative value. So in other words, this is our table. When it comes to the square root, we have to adjust just a little bit in what we use as our inputs. We use 0, 1, 4, and 9 instead. Let's graph and see what this looks like. 0, 0, 1, 1. Then we're at 4, 2, and then we're at 9, 3. Make sure you make a nice curve here. And that is what our square root parent function looks like. Okay, we do have an x-intercept. We are still touching at 0, 0. Same for our y-intercept. Let's think about our domain. So our domain left to right. We start at 0 included, and we go to infinity. For our range, we start at 0 and go to infinity, so same as our domain. Still no asymptotes. And technically, we can say that we do have a minimum at 0 because that is our lowest point, period. Now this is not symmetric. There's no way to fold this so that it falls on itself, so we would say none. Okay? Moving on to our cubic parent function. Our cubic parent function is f of x equals x cubed. Again, we don't know what's going to happen, so we will still proceed with our normal table unless, like we just saw, are forced to do otherwise. So let's begin. F of negative 3 means plug in negative 3 as an input, and cubed means to the third power. So that means, in other words, negative 3 times negative 3, which is 9, times negative 3 again, which is negative 27. F of negative 2 means negative 2 3 times, giving us negative 8. And then so on, negative 1, 0, 1, 8, and 27. Now this one, we're going to be limited on what we can fit, so we fit as much as we can. 0, 0, 1, 1, negative 1, negative 1. However, next we go from 2, 8, and negative 2, negative 8. However, we cannot fit the 27. So that is fine. Just make sure that when you draw your graph, when you get to the middle, you don't just do a straight line. There is still a curve going on. Sorry about that. Let me try that again. There's a curve going on in the middle as such. So make sure you're drawing your cubic function appropriately. All right. Still our same intercepts. Nothing's changed yet. Our domain, even though it looks narrow, eventually we will keep going, negative 4, negative 5, and then same on the right. So for that reason, we are still talking about from left to right, we're still talking about all real numbers. And then that's even more obvious to see with the range that we go. Negative infinity to infinity. Because of our range being negative infinity to infinity, we will not have a maximum or minimum. And then if you were to try to fold this, it'd be another one where if you fold it twice, just like the linear, it would fall on itself. So we're going to say it's symmetric across the origin. All right, moving on to the cube root function. Now, there's a good chance this is the first time you've heard of the cube root function. So for the cube root function, it looks something like this. It's f of x, but instead of a square root, we have a cube root. Here's what that means. In this little check mark, we put a tiny little 3. So that's the difference between how we write square root versus cube root. Just a little 3 there. All right, we're still gonna at first. So again, this is another one where you might hold off before you start copying this. I'll try the same thing and see if it forces me to do otherwise. Here's how the cube root function works. Let's think of 0. So f of 0. When I take the cube root of 0, unlike a square where it asks what times itself, it's what 3 times gives me 0. Well, 0 times 0 times 0. So this is 0. Let's try 1. Well, 1 times 1 times 1 is 1, so 1 again. Let's try 2. If we do f of 2, that means what 3 times gives me 2? Well, it's not a pretty answer. So what that means is we also have to adjust these inputs to give us something that makes more sense. So let's think about it. What's the next thing up that 3 times you'll get that? Hopefully you're thinking 8. Here's what that means. What 3 times gives me 8? Well, 2 times 2 times 2 does. So that means cube root of 8 is 2. The next thing up, which we won't be able to fit on the graph, but we'll put on here just to have, is 27. Cube root of 27 is 3. Moving on backwards, we had an issue when we took square roots of negatives. We want to see if we have an issue when we take cube roots of negatives. So let's think to ourselves. What 3 times gives me negative 1? Hopefully you're thinking that negative 1 times negative 1 times negative 1 does. So f of negative 1 is negative 1. At this point, we just go backwards. We use negative 8, so cube root of that is negative 2. And again, even though we can't fit this one, let's just go ahead and include it. Let's graph and see what this looks like. And notice how you will definitely need to use at least these 5 points. Otherwise, if I were only to use the middle 3, it could be a line, it could be a cubic, and now it could be a cube root. So you have to include one more pair, which would be 8, 2, and negative a, negative 2. Now when connecting this, think of a sideways cubic. That's exactly what it should remind you of. There's actually a relationship between the two that we'll study next unit. So there's a reason why it looks like a sideways cubic. Let's fill in our information. We're looking at negative infinity to infinity on both domain and range, with still no asymptotes just yet. Still no maximum or minimum. And also symmetric across the origin. Now the notation I just used for my asymptotes in max and minimum is called the empty set, and it's just another way of saying none. And that is our cube root function. We will continue with our last 3 in the next video.